Welcome to the Crazy Hat Chemist. So another video here on Thermochemistry Part 2. So let's get moving. Bam! So today we are talking about Gibbs Free Energy calculation number 2. We got a lot of information in this video here and a great graph. So really pay attention to what I'm giving you. Okay, I also got two hats. Two hats at the end because this is calculation number 2. That makes sense? Alright. So, we're going to determine the delta G naught for the decomposition of baking soda at room temperature. So here's the equation, the balanced chemical equation for baking soda, which is sodium hydrogen carbonate. Okay, so I got 2 moles of sodium hydrogen carbonate, that's a solid. I need to input some heat energy, that's why the delta above the arrow, to make this reaction proceed forward, so that I got on the product side sodium carbonate, that's a solid, plus carbon dioxide gas, plus H2O gas. Notice that there's more moles of gas on the product side, so there's more disorder on the product side. Hopefully that makes sense. Okay, the enthalpy change for this reaction is 135.49 kilojoules. Okay, is this an endo or exothermic process based on that numeric value? Really, it's based on the sign. And from our previous videos, you should be able to answer this question here. Okay, since the sign of this enthalpy change is positive, this is an endothermic or heat-absorbing reaction. Therefore, the heat term belongs on the reactant side. Okay, and the entropy. So the S naught term for the reaction is 334.0 joules per Kelvin. Okay, what does the sign of this indicate? Well, since the sign of the entropy term is positive, this indicates that the products have more disorder than the reactants, i.e. there are more moles of gas produced on the product side. And I aforementioned that as I went over that balanced chemical equation. There is 1 mole of carbon dioxide, 1 mole of water vapor, and there are no moles of gas on the reactant side. All right, so here's our delta G naught for the reaction is equal to delta H naught for the reaction minus T delta S naught for the reaction. We're going to solve for delta G here to determine Gibbs free energy. Okay, so what we're doing is we're plugging these values. For the enthalpy term, it's 135.49 kilojoules minus our 298.15 Kelvin. Again, this is at 25 degrees Celsius, which is at room temperature. Okay, so we added our 273.15 to the 25 to get the 298.15. We have our S naught term at 334.0 joules per Kelvin, and then we have to do that unit conversion just like we did in the previous video, and that is go from joules to kilojoules. This way we can sum up the entropy and the enthalpy terms together. Then, when doing all the math, we get this value of 35.9 kilojoules. Then we're going to look at this value here, and we're really looking at the sign in front of the value. This is a positive number, so that should be telling you something. This is different than the previous video. The previous video was exactly opposite this. So we should be able to answer the question, is this a spontaneous or a non-spontaneous reaction? And it is totally entirely based on the sign of the Gibbs free energy value, which is the delta G naught for the reaction. Since the sign for the Gibbs free energy is positive, the reaction is non-spontaneous and reactant favored. That's why you actually need to input heat to make this decomposition reaction proceed forward. Otherwise, you can have baking soda, sodium hydrogen carbonate right on the bench top, and nothing's going to happen at room temperature. Okay, so the question is, what is driving this reaction? What is the driving force for this reaction? Is it the enthalpy or is it the entropy? And so we're going to find out which term is corresponding to the Gibbs free energy. The Gibbs free energy is reactant favored or non-spontaneous. Which of the two terms is it that is non-spontaneous and reactant favored? It is the enthalpy term or the entropy term. Okay, so the enthalpy term being positive and the entropy term being positive are of the same sign. So without doing the math, I cannot figure out which direction it's going. Because they are of the same sign, they are opposing each other. However, since the enthalpy term is larger than the entropy term, the driving force here is enthalpy. Hopefully that made sense, because the enthalpy term is an endothermic process. That means that reaction is reactant favored, and the enthalpy, the delta H, is on the reactant side. That 135.49 kilojoules would be placed on the reactant side of this equation. I'm not done. We got a lot more yet to do on this problem. Okay, so we're going to determine the delta G naught for the reaction, that's Gibbs free energy for the reaction for the decomposition of baking soda at baking conditions. And this is normal oven temperatures, which you do things baking wise, and that's 350 degrees Fahrenheit. I've converted that into degrees Celsius. That's 177 degrees Celsius for all of you math people. Okay, so now you should understand that baking soda is used in baking, and there's a reason that we use baking soda, so that we can get carbon dioxide and water vapor, essentially a lot more carbon dioxide, so that we can make things that are baking expand and rise, because otherwise we have unleavened bread, and that's not fun. We want bread that expands, or baking that expands. Therefore, we need that carbon dioxide gas and the water vapor gas. Okay, so that's that same equation that we talked about before, which is 2 moles of sodium hydrogen carbonate produces sodium carbonate, carbon dioxide, and water. Okay, so the delta H naught for the reaction is 135.49 kilojoules. It's the same value that we had before. Is this endothermic or exothermic? Well, we already answered that question, but we can answer it again. Since the sign of the enthalpy change is positive, this is an endothermic process, and that value 139.49 kilojoules belongs on the reactant side. Okay? And the S naught for the reaction is 334 joules per Kelvin. We actually have the same value for this. All we're doing is we're changing the temperature here. So what does the sign indicate? So there's a reiteration of what we had before. Well, since the sign of the entropy is positive, this indicates that the products have more disorder than the reactants, i.e. there's more gas on the product side because there is no gas on the reactant side. So we're going to plug these values in with our new temperature. So we're going to take our 177 degrees Celsius plus 273.15, and we're going to come up with our Kelvin temperature. And then we're going to plug in our enthalpy, our entropy terms. We're going to make sure that the units cancel out, and we're going to convert our entropy term, that's the delta S, into kilojoules. So I plug these values in. The enthalpy term is 135.49 kilojoules like it was before. I have 450 Kelvin as my temperature. I got my 334.0 joules per Kelvin as my entropy term, and then converting that joules into kilojoules, I'm going to divide by 1,000 joules. I'm going to sum all this up here, and I'm going to get this value at negative 14.8 kilojoules. Okay, now this is very important here, because at negative 14.8 kilojoules, we should know that there has been a sign change for Gibbs free energy. Okay, is this a spontaneous or non-spontaneous reaction at this elevated temperature at baking conditions? Well, Gibbs free energy is negative. Therefore, this reaction is spontaneous. This is why we bake things at 350 degrees or 177 degrees Celsius, so that we produce, from the baking soda, we produce gas, carbon dioxide, and that makes our baking items rise. And then what is the driving force for this reaction? Well, the driving force for this reaction, the enthalpy and the entropy, both being positive, they're opposing each other. However, since the entropy term is larger at this elevated temperature, that means that the driving force is entropy at higher temperatures. Okay? So, as you increase the temperature, that entropy term becomes larger and larger and larger. So look at that equation, delta G equals delta H minus T delta S. It's really important that you understand this. We are multiplying the entropy term times the temperature. So as the temperature increases, that T delta S term gets larger and larger, and eventually there's a switch between non-spontaneous and spontaneous with elevated temperatures. This almost occurs at all reactions. Okay, now what we're going to do is we're going to take a look at this graphically and actually figure out where that switch from non-spontaneous to spontaneous occurs. So we're really tying in the first calculation, number 1, so that you understand that first. Then we're doing this calculation, number 2, at 2 different temperatures, and then we're going to graph it and figure out what that exact temperature is. All right. So we're going to graph the previous data that we just did on those 2 equations. Okay, we're going to assume that the change in the enthalpy and the change in entropy are independent of temperature. Then Gibbs free energy is a function of temperature. So we're going to make that graph of Gibbs free energy and temperature. And here's this graph. On the y-axis, you should see Gibbs free energy in kilojoules. On the x-axis, you should see temperature in Kelvin. And I have graphed with 2 points, 2 blue dots, and then a black line in between here, the 2 points that we just did at 2 different temperatures. One was at room temperature, one was at baking temperature at 350 degrees Fahrenheit. Okay, so delta H and delta S are both positive. We got that from doing this calculation before, so we know that they are opposing each other. Here are these 2 values here. One's at room temperature at 298, one is at 350 degrees Fahrenheit, which is 450 Kelvin. Okay, and we got 2 different Gibbs free energy values that we solved for, and then we've plotted the temperature versus the Gibbs free energy, and we plotted these, and then we've connected the dots. We've got ourselves a line. So now what we're going to do is we're going to manipulate the Gibbs free energy equation just a little bit. So this is the Gibbs free energy equation. That's delta G, Gibbs free energy, is equal to delta H minus T delta S. So what we're going to do is move the terms over just a little bit, move things around on the right-hand side of this equation. So I've got delta G is equal to negative delta S times T plus delta H. Okay, this will allow me to rearrange this just a little bit more into this y equals mx plus b format. So that's why I'm writing it in this format, so that we can take a look at these 2 points where I drew the line. Now, really what we want to do is figure out what is the y-intercept. So what is the y-intercept? What we need to do is extrapolate this line of which we have drawn with the 2 blue dots and the line in between the 2 blue dots. We need to extrapolate this line until it hits the y-axis. So I've done that here with this red dashed line. So with this red dashed line, I've extrapolated the line that I had, so that I have now the y-intercept. It interacts with the y-intercept there. And this is the delta H naught term. Okay, so hopefully that makes sense, because we have y equals mx plus b. Now, what is the slope? The slope, if you look at that y equals mx plus b and how I have this, the slope is going to be negative delta S naught. So we have the y-intercept, we have the slope. Hopefully that works. Okay, now where I've drawn this blue line right here, okay, at 0, that's when delta G is 0, which is at equilibrium, and that is where the switch occurs. Okay, so you should see that there's a Gibbs free energy that's positive above the line and negative below the line. That blue line is indicating equilibrium, when Gibbs free energy is 0. So above the line, the delta G naught is positive. That is greater than 0, and that is non-spontaneous. Okay, and then below that blue line, okay, when the delta G naught is less than 0, that is spontaneous. So the switch occurs when delta G naught is equal to 0, which is at equilibrium. That's what we need to solve for. So the question is, what is this temperature of which this switch occurs? Right? This switch occurs between a positive non-spontaneous delta G naught value and a negative spontaneous delta G naught value. So we're going to figure out what this temperature is, because we need to actually have our baking conditions at least at this temperature, if not greater than this temperature. Anything greater than it would work. Okay, so we're going to solve for this numeric value here by plugging in some information. All right, so what is T star? T star is the switch. Okay, so T star is the temperature at which the, quote, switch occurs between spontaneous and non-spontaneous, non-spontaneous, spontaneous. So we're going to solve for T star. Okay, so I included the switch between spontaneous, non-spontaneous, or spontaneous, non-spontaneous. It doesn't matter, right? Spontaneous, non-spontaneous, non-spontaneous, spontaneous. Doesn't matter. Okay, so delta G naught is equal to delta H minus T star delta S. So we're going to rearrange this and solve for T star. So at equilibrium, Gibbs free energy, remember, is equal to 0. And that's when this switch occurs from spontaneous to non-spontaneous or non-spontaneous to spontaneous. So I've replaced the delta G naught with 0, indicating that we're at equilibrium, and then therefore I can solve for this switch of the equation. I've rearranged the T to solve for T star. So T star is equal to delta H over delta S. Okay, hopefully you can do that all on your own. You're going to subtract the delta H on both sides, then divide by negative delta S, and then the two negative signs disappear, cancel each other out, and you get the T star is equal to delta H over delta S. We're going to plug in the values here that we had, and that is making sure that the units cancel, and I've done a little bit of unit canceling for you. So for T star, the delta H term is 135.48 kilojoules. I've converted the entropy, the delta S term, to kilojoules per Kelvin. That way the kilojoule term cancels out. So I got 0.3340 kilojoules per Kelvin. I've solved for T, and I get 405.6 Kelvin. So notice that this value corresponds to the intersection of where the graph crosses the y-axis on the previous graph, right? So the x-axis, sorry, on that previous graph, right? So hopefully that makes sense for you. Okay, so you should see that it crosses right there, and that's when that switch occurs between spontaneous and non-spontaneous. Okay, so this is where we have on the x-axis, we have that switch between the 0 and the non-zero, either positive or negative. Okay, so reiterating, delta G naught is equal to delta H minus T delta S, and we got that T star. Okay, so this is just like a summation of this entire information here. If the enthalpy term is less than 0 and the entropy term is greater than 0, notice that they're opposite in sign, then the delta G naught is less than 0 at all temperatures. That's why we can make this prediction. When they are opposite in sign and the enthalpy is negative and the entropy is positive, we know that it is a spontaneous reaction. Okay? It's always spontaneous. If the enthalpy is positive, that's endothermic, and the entropy is more ordered, that is negative, then the delta G naught for the reaction is positive at all temperatures, and this means that it is always non-spontaneous. Okay, again, the enthalpy and the entropy are of opposite signs, so we can make that always prediction of non-spontaneity in this particular case, when delta G naught is positive greater than 0. Okay, if delta H is greater than 0, that is endothermic, and the delta S is positive, that is more disordered. Notice they're the same sign here. Then the G naught for this is less than 0 when the T is greater than the T star. That's where the switch occurs. Okay, so it depends on that temperature. When the delta H is less than 0, negative, and exothermic, and the entropy is less than 0, that's more ordered, then the G naught for the reaction is less than 0 when the T is less than the T star. And that is what it depends on. It depends on that switch. So take a look at this slide. There's a tremendous amount of information here within this entire lecture here today. Okay. I am the crazy hat chemist, and you've got to figure out what side of the battle you are going to be on. Are you going to be on the English side, or are you going to be on the pirate side? So you got to figure out which side of that equation you're on. And maybe, depending on the times, you might have to make the switch between one hat and another hat. And are you a pirate, or are you not a pirate? And the case is, with the enthalpy and the entropy, whether you are a pirate or not a pirate. Okay? If you like that video, give me a thumbs up. Please subscribe to my YouTube channel. Pass on my information to anybody that needs help in chemistry. You can find me on my website and get a cool sticker or a cool t-shirt designed by my son. Hats off to you. Figure out what side of the fence you are on, and I'll see you next time. Bye for now.